All right, how's everything going? Pretty good. How's Zenity working? Any issues? So we have a short week this week. We got today and tomorrow, and that's it. So you definitely want to discover and ask about Zenity issues today or tomorrow, if possible, because then it's like 5 days till we're back. And you want to be able to get some work done on it, presumably. So good to go on that. All right, so let's talk about PA4. So PA4, by and large, pretty good work. This was clearly the hardest programming assignment, right? And PA5 is a group assignment, and you got to figure out Zenity, but PA5 isn't really all that bad. It's a bash script, and you can split it up amongst people. So PA4 was definitely like the worst of all the programming assignments in here. So what made PA4 so difficult?
Working with get-tar instead of like f-gets and scanf. And
So you're doing very low level input, right? You really got to read a character at a time and process things character by character, and that's different. It's not like just grab a line and scan it, right? So you're sort of putting those things together yourself. So that makes it a lot more complicated.
Most complex one.
Yeah. So what else made it hard?
There were way more test cases.
Yeah, so way more possible test cases. And when I did my testing, I tested on a variation of the original test case from the assignment, right? And I had a shorter one with some other challenges in it, and I did War and Peace. And in some cases, program worked perfectly on all of those cases, right? And that's probably 100%. In a lot of cases, it blew up on War and Peace, but it worked perfectly everywhere else. Okay, so that's like 5 points. In some cases, it worked pretty well on those other tests, but had one or more of the following issues. It might not be ignoring things like parentheses, but using them to mark the ends of phrases, or to throw a seg fault or something like that, right? Instead of just completely ignoring them. It might be doing something that's causing it to see empty phrases that aren't actually there. And when the final phrases print out, it says, there's 15 occurrences of this empty phrase that has length of 0. And that's just some kind of edge case in the processing. Or it might be doing something like, ignoring other characters, like number signs don't get any special treatment, but sometimes the code dumped number signs, things like that. But by and large, if it kind of worked more or less on any of the tests, it worked on all of them except possibly War and Peace, right? Which is going past 1,000 phrases, past 200 characters. But I don't think I ever encountered a case where on this test it seemed to work really well, and then on this test it totally failed, right? It was a little bit of an all or nothing. And in some cases, the phrase count's not coming out right, something's not getting reset to 0 maybe, stuff like that, or something's not being initialized in some other way. Anything else that made this trickier than others? The counter? Keep count of phrases? Yeah, so there's if you're not using a structure, it's parallel arrays, and it's another thing to keep track of, right? So array of phrases, array of counts, and anything you do over here, you got to do over here, right? You add a new phrase, you got to make a new entry over here, and when you sort, you got to do your swaps in parallel, right? If you swap these two phrases, you got to swap those two counts, and so on. So that's another layer of complexity. Some people still were getting tripped up with trying to pass this two-dimensional array, this dictionary, and sometimes I'd look in the code and there'd be, a car star, a dictionary, bracket, or stuff like that. And I really tried to make it so you didn't have to do that. You never had to use a star, you never had to use an ampersand, you never had to use any of that stuff in passing things, because your dictionary was 1000 by 201. You can define the argument as a character 1000 by 201, right? And you don't have to worry about pointers and dereferencing and stuff like that. Overall, it looked like when the code was not working, in most cases, it seemed like people were trying to do too many things inside one or two functions. So there might be, something calling getCar, and then looking to see if it's a character that should be ignored or if it's a punctuation. And inside the loop that was calling getCar was code to build up a phrase, and that was wrapped inside another loop that was taking the phrase and looking for it in the dictionary, and that was wrapped inside an if-then that was saying if it's not found in the dictionary, let's make a new phrase. And then there was stuff outside that to look for 1,000 phrases, and there was stuff to look for EOF, and it was all a bunch of nested loops inside a main program, right? And the reason that I keep talking about modularizing, about breaking things into functions, because that helps you organize your thoughts, right? It helps you take a problem and break it into subproblems. At some point, you can take a huge gargantuan problem, you can just start banging out code, and you can write 10,000 lines of code that solve it, right? That's fun, if that's your thing, right? But it's almost always easier to write 20 or 30 lines of code that do this, instead of 1,000 lines of code that do all of this. And so when I keep talking about modularizing, it's the idea of how do we break this problem into subproblems, right? Our problem is to read input, do some processing, break it into phrases, count the phrases, print a sorted list, right? But can we break that into 2 or 3 or 4 smaller problems, and then tackle each of those and put those together into a main program? And so a smaller problem is, well, we have to build up a phrase, right? Well, can we break that into 2 or 3 or 4 subproblems, which is, read characters till we find the beginning of a phrase, read characters and save them until we find the end of a phrase, add a null terminator, right? And can we break those steps into smaller pieces? So read a character means read a character, loop if it's a parentheses until it's not a parenthesis, convert white space to space, make things uppercase. Can we take that and break it into these smaller steps, right? So it's not just trying to come up with as many functions as you can, it's really trying to reduce the size of each problem that you have to code a solution for. Right, so all I'm doing is making my super get car, all I'm doing is making my phrase recorder, all I'm doing is making my sort routine, right?
About that, so I'm kind of curious, because I know you've always said that I don't know the best way, but one of the best ways to do it is to code essentially the main function first and leave placeholder functions, and then later on fill in the functions. So I found, at least for me, what works is to do it the other way around.
Yeah.
Where I think about what functions I'm going to need, and then I can debug it easier that way, because I don't have to worry about testing it outside of main. I can just do it in main before I make main.
Perfect. Yeah, so there's this idea of top down, bottom up. Top down, you start with main and you just call these functions that don't exist and you keep working your way down. Bottom up, you start with, okay, here's my getCar function, or here's my function for swapping 2 phrases in my dictionary. And I'm going to use that and I'm going to build my sort function. And that is easier for debugging. And that also goes along well with kind of object-oriented design, which is where we're heading in spring. Because those low-level pieces are usually pre-made for us.
The other question I had was that, so you said make a getCar function, but that function already exists. So did you mean make it a function with a different name?
Like your super getCar.
Yeah, okay.
Yeah.
Gotcha.
The super duper getCar, as we kept calling it.
Oh.
So let me...
I spent hours trying to find a way to edit an existing function or something like that.
Oh.
I don't do it. It's like, maybe he just wants me to just do my own unique function.
So I'll show you a solution that includes the super duper getCar.
I think I call it mine car get or something like that.
Okay. So main program right?
Mhm.
So I work off mainly 4 functions, and I prototype them here. And the dictionary and the count array, those are just hardwired dimensions, right? They're just going to expect something that's 1000 by 201. Buffer is just a temporary string, so I just use a char star for that, but I could have hardwired it to 201 also. So main program declares dictionary that holds the actual phrases, the count array that tells me how many times each phrase occurs, so count and dictionary are the parallel arrays, and then dictionary length tells me how many entries I have in my dictionary. Okay, so if dictionary length is 0, there's nothing in my dictionary. If I have one phrase, dictionary length will be 1, which means the last entry in my dictionary is index 0. If dictionary length is 5, I have 5 phrases, which means my dictionary entries are index 0, 1, 2, 3, and 4. Okay, so up front, I want to make sure I understand how dictionary length and dictionary and count relate to each other, right? My last valid entry is dictionary bracket, dictionary len minus 1. The corresponding count is count bracket dictionary len minus 1. And an empty dictionary is when dictionary length is 0. And that's kind of standard for all these arrays, right? If your string array has 6 entries in it, the last entry is index 5, and so on. So read phrase reads from standard in, finds a phrase according to the definition, loads it into buffer. So every time I call read phrase and I pass it this character array, when it comes back, that array buffer should have the next phrase from my input. Okay, and I can test the heck out of that by itself without doing anything about tallying phrases and so on. And the way I wrote read phrase, it also returns a true or false. If it finds a phrase, it returns true. If it hits end of file, it returns false. So I wrap all this in a while loop that basically says while read phrase is true. Now what do? I call my tally routine. So I pass it the new phrase, the dictionary, the count array, and the length of the dictionary. And tally's goal is twofold. One, it looks in the dictionary for the phrase, and if it finds it, it bumps up the count. If it does not find the phrase in the dictionary, it will add it to the dictionary, and it will return the current dictionary length plus 1. So tally always returns the length of the dictionary after it's done whatever it has to do. So I update the length by just saying dictionary length equals tally.
So you said that read phrase returns a Boolean, true or false?
It's a 1 or
That
0.
was my confusion.
Yeah.
because I was like, it's, okay.
Yeah. And I could have just passed the address of dictionary len, but I don't like ampersands. So, or I didn't when I wrote this.
So in
so.
C, while will recognize a 1 as true. You don't have to
C will recognize anything non-zero as true.
Oh, okay.
But be really careful with that, right? Because some languages we think of 1 as being true and anything else as being false. For C, anything that's non-zero is true, right? So scanf, if you check the return from scanf and you just say if scanf, that'll be true if scanf returns 1 or minus 1 or 2 or 3, right? It'll only be false if it returns 0, and that's usually not what we want. All right, so there's the whole phrase reading, building the dictionary loop, right? It's one statement in a while loop. So read a phrase, tally it up in the dictionary, and just keep doing that until read phrase comes back and says I hit end of file. And then you just call your sort and your print. Okay, so that's the main program. Read phrase, so there's a few routines in here. There's my super duper get car function, and there's a function that tells me if I've hit the end of a phrase terminator. So this just tells me if my character is a period or a comma, and so on. And then read phrase returns 1 for success, 0 for end of file, and it loads a phrase into a buffer. So first thing you do is you look for the start of a phrase, right? So call my super duper get car. If it's a space or it's a punctuation mark, call get car again and just keep looping in here. Okay, with an extra check, if I hit end of file, I return 0. And that'll tell my caller that I hit the end of the file. Otherwise, this loop just skips over spaces, periods, commas, semicolons, more spaces, and so on. When I come out of this loop, I know that C is the first character in my phrase, because it's something that's not a space, not a punctuation. So I save that in my output buffer, right? Initialize the index to 0, save it in the output buffer, bump up my index. And now I go into my second loop, which basically says, get a character. If it's not a punctuation, if it's not a terminator, store it in my array. Get another character, keep doing that. And the only trick in here is I do a little bit of a cheat. After I store a character, I bump up my index. If my index is 200, which is where I need to store my null terminator, I just bump it back down to 199. So I just keep replacing the last character in my phrase until I actually hit the end of the phrase. So that stops me from blowing up my phrase array. So when I come out of this loop, I must have hit a terminator. Right, I read a character and there was some kind of punctuation, a period, a comma, etc. So at that point, I throw a null terminator on my string and I just return a 1 saying, hey, I've got a phrase for you. So that's the whole phrase ingest, right? And it's really two pieces. Look for the beginning of a phrase and then look for the end of a phrase. And while you're moving to the end of the phrase, save everything that you're picking up, right? And my get car means I'm not worried about, if this is a tab, change it to a space, make this uppercase. If it's a parentheses, ignore it, so on and so forth. Because my get car is doing all of that processing for me. Right? I know my get car is returning only uppercase letters. It's not returning characters I want to ignore. And the only kind of space it's returning is just a single space. Right? New lines, tabs, all of that are converted to spaces. So I can use its space up there. All right, so super duper get car, we've gone through this in class, right? Basically, get a character. If it's something that you want to ignore, get another character and keep looping. So this loop is skipping over those things that we want to ignore. And then this should probably say if is space C, but I just did a new line. But if C is a space, change it to a single space. Convert it to an uppercase letter if it's a letter, and then return that value. And if I read end of file from getCar, right, when I get down here, I'll be returning end of file also. Because EOF is -1, it won't match any of these, so I'll kick out. It won't be a space. It won't change when I convert to 2-upper, and I'll just return EOF. So my getCar is just like getCar, except it ignores certain characters, makes things uppercase, and changes white space into a space. And then isTerm tells me if I have a terminator, a punctuation mark, and it's just a big if statement. So, and I decided to treat end of file as an end of phrase. So in this case, if your phrase ends without a punctuation at the end, EOF will terminate the phrase, and you'll pick that one up. But that was optional. And then tally, which does all the work for saving a phrase in a dictionary. So buffer is the new phrase, there's the dictionary, there's the count array, there's a length of the current dictionary. So first part is loop through your entire dictionary and see if your phrase is already found. So for each entry in the dictionary, string compare my current phrase to entry I in dictionary. If string compare returns 0, the phrase matches, so bump up the corresponding entry in the count array, and the dictionary length is still what it was before this, so we just return dictionary length. If we come out of this loop, it means we've gone through all the entries in the dictionary and none of them matched our phrase, so we have a new phrase. So first thing I do is if our dictionary already has 1,000 things, I just return 1,000, right? So I read the phrase, I ingested it, but I just didn't store it. Right, so that stops it from blowing up on too many phrases. Otherwise, we've got space in our dictionary. So copy my phrase into the next location in the dictionary. store a 1 in that location in the count array and increment the length, and then return the new dictionary length. So that does the recording of phrases. And then printing is just loop through the dictionary, print out each entry. All right, and again, dictionary len is the number of things in our dictionary, so print out the count and the phrase. And then sorting is a bubble sort. So a pair of nested passes, compare the length of the subsequent phrase to the current phrase, and if they're out of order, this swaps the phrases, and this swaps the corresponding count entries. So that just orders the output. So test files, this was pretty much the original test file from the assignment, but I added some extra challenges. So multiple terminators after hello, and after file, parentheses which should be ignored, number signs which should not be ignored, and so on and so forth. So that was one test. That was just a phrase broken up across multiple lines, just a quick check on new line handling. And then, of course, War and Peace. So questions about any of that? Say again?
Or is that just showing the format?
I didn't hear the first part of the question.
Never mind.
Okay. Yeah, this is just the input file. All right, so I posted comments along with your grade. If there were deductions, I gave you at least some sort of explanation for what the deduction was for, but I was copying and pasting from a list of deductions, so if you didn't understand what it meant, let me know. And in some cases, I said, let's go over this next week if you want to. So I strongly recommend trying to figure out if you had any lingering issues with PA4, try to figure out how to fix those, right? This is typical of what we'll see in 222. Okay, there are going to be larger programming assignments in there, and they're going to be very sort of hierarchical. We're going to be learning new concepts, right, new for most of you, in data structures. So we'll be working with linked lists and binary trees and AVL trees and all these other things. So there's going to be this layer of learning these new ways to organize information. There's going to be technical layers of dealing with pointers and dynamic memory allocation and freeing memory when we're done with it, and building up these fairly complex structures that contain other structures inside. So there's going to be, technical mechanics of doing these things in C, and then there's going to be kind of organizational challenges of here's what we want to do, but we got to break it down into these pieces. So this idea of breaking big problems into small problems will necessarily come up again and again in winter and definitely in spring. So it's worth getting some more practice with it before then. So if you want to go over your PA4 or anything else, right, let me know. It's a little crazy right now mornings because I've got lots of people coming in for last minute advising for registration, but that should stop pretty soon, and then people are theoretically registered for spring too, so it should calm down for a while. But shoot me an email and we can figure out a time to talk. All right. So I want to talk about arrays in Bash, and this may be something that you find useful in PA5. So I want to talk about arrays, regular arrays, I want to talk about associative arrays, and I want to talk about two utilities, awk and sed. And I'd like to get through these today and tomorrow, and then when we come back from break, we'll talk more about awk and sed, and then we'll go on. We'll be in week 9 by then, so so the end will be coming quickly. Are we in week 9 now? We're in week 9, so we're going to be in week 10 next week. So, so we'll pick up some other topics then. Let's talk about arrays. So you know what arrays are in C, right? They work kind of the same in Bash, but easier. Right, we can say variable bracket some index equals value, and that creates an array. That makes variable an array, and it stores that value at that index. And we don't really need to declare anything. Arrays just kind of happen for us. So, so what should we call our array? Give me a good name.
James.
James? Okay. Right. And so when you want to print out the value of an array element, it's $ curly bracket, variable name bracket index. So James bracket 2 is 222. We could set James bracket 7 equal to, we'll set it to 49. And now if I look at James bracket 7, it's 49. If I look at James bracket 2, it's still that value. And arrays are handled internally by Bash, and it's pretty clever how it does it. So let me just put this down. So if you want the value of variable bracket index, it's that funny notation, $ curly bracket, var bracket index. But I can do something like this. All right, so it's a really big looking array. Right, but it's actually like got that value in there, and not that one, and not that one. So has it actually allocated that much memory? Obviously not, right? But somehow I can have these ridiculously large indices in my array. Whether that's a good thing or a bad thing, I don't know. But there it is. And that looks a little magical, but it's actually not. Once we talk about this next thing, which is an associative array. So associative arrays are awesome, okay? They are one of the coolest things in programming languages, in my opinion. When I first learned about associative arrays, everything became a problem in associative arrays for like a year or two for me. Anything I wanted to do, I found a way to do it with associative arrays. It was just like my super hammer. Just like every problem, it's like, wait, I got that, bang. Associative array to the rescue. It's a really powerful concept, okay? So we can declare an associative array as follows. Declare -a, and then whatever the name of our array is. So I'm going to make an associative array called hammer. All right, hammer's an associative array. So I can do hammer bracket 2 equals, and I don't know, I'll just store some stuff. right? So it looks like a regular array, right? But I can also do things like this. And now I've got an entry indexed by the name Nick. And Nick is not a variable, right? It's not like Nick is equal to 17 and it's storing this at index 17. Nick is just a string, right? And entry Nick of this array is called ha ha ha. Alright, so now I have an index in my array called what question mark. I put it in quotes so that the shell wouldn't eat the question mark. Have an index entry called what? Right. So associative arrays you can index with anything, not just integers. We can index it with strings. Let's see if we can go crazy. Right, so there's entry number sign, dollar sign, percent sign. So it's like a super array. It's an array that's way more general than a traditional array, which is only accessed by typically consecutive integers starting from 0. With an associative array, the indices can be anything we want.
So, for example, if you define an associative array with 3, so there's 4 spots in the array, then where would this go in terms of memory in those 4 spots?
It figures it out.
It just, okay, so you can't tell it which of those 4 to go
No,
into.
no. So I didn't specify a size. I just said declare an associative array named hammer right at the very top, right? And theoretically, I can store as many things in this array as I want.
Well, I thought you declared the size.
Yeah, no, I never specified a size.
Because what I'm thinking about is, let's say you do declare a size, and then...
There's not really a way to do that,
Oh, okay.
right? So it's simply an array, just like with a non-associative array, right? I didn't specify a size. I just made it an array by storing things at indexes, but I could have a crazy index like that, and it still works.
Okay.
But that's clearly not the size of the array, right?
Yeah.
So why are associative arrays so cool? What are they good for?
Because you can use the value of other variables for locations.
Yeah, you can use the value of other variables for locations.
I had a question with this. Is this similar to a dictionary or a hash map?
It is a hash map. Yeah. Right, so here's a list of 3 teachers, and I've stored what area they teach inside this array. So I can say read name, and I can say Izad, and I can say echo $hammer bracket $name. And it shows me Izad teaches EE. And if I say Tina, and I echo that, it tells me she teaches mechanical engineering. And if I say Nick, it tells me that I teach CS. And if I put in someone who doesn't exist, it'll come back and say, well, there's no entry for that name. All right, so it gives me a blank. So I could store, information about people. I could index that information with a person's name, and I could store whatever I wanted. Right, I could have a space-separated list of courses they teach, or grades that they've gotten, or classes they're taking, or whatever. And there's theories that this is basically how our brain is organized, right? It's pretty clear if you think about your memory, that your memory is not just a big sequential array that's indexed with integers from 0 on up, right? Because it would be horrible to try to find something in there. Try to remember this person's name, and you just got to start checking each entry in your array, right? But an associative memory, right? That name could be associated with, you know, something about the person, right? I played soccer with this person in 3rd grade, and now you put in, you know, 3rd grade soccer, and there's a list of people that are associated with that, and it's like, oh yeah, that's the person, right? Our brain seems to work arguably by making these associations between pieces of information, right? So a network of some sorts. And that's really what this kind of thing supports. If you were doing PA4 in Bash, you could make an associative array called dictionary, and each time that you get a phrase, you could say, okay, use that phrase to index my dictionary, and what you could store in there is the number of times you've seen the phrase. And now when you want to tally a new phrase, it's just, you know, plus plus dictionary bracket phrase. And if that phrase has occurred before, it'll pull out the current count and it'll increment it by 1, right? And you don't have to do all of this string compare and all that kind of stuff. So these are really powerful constructs. Now an advantage of a regular array is if we want to access everything in it. For example, when you want to print out your dictionary of phrases, you just print out dictionary bracket 0, bracket 1, bracket 2, bracket 3, and so on, right? We can't really do that here because we don't know what the indexes are, right? Unless I know that I have an index named Izad, how am I going to know that I should print hammer bracket Izad? Right? We've got to know what the keys are if we want to dump out a list of all the information that's in this associative array. So there's something we can do. We can say echo $ parentheses. Say again? Yeah. Let me show you this, see if this answers it. So if I do exclamation mark name of the array and I ask for element @, that says I want a list of all the keys inside this array. If I do that, I get this space separated list of keys. I'm going to get in trouble with my fancy keys, I can tell. I should not have done this. And if I do this without an exclamation mark, I get the list of corresponding values. So this will probably, yes?
Is it possible to remove some of the indexes, like your fancy keys?
Yeah, I don't know how to, I mean, I could change it to, let's try that. Yeah, it didn't get rid of it though. There's probably a way to delete it, but I don't know what that might be.
Is the first one the keys or the index?
So this, with the exclamation mark, that's the keys. Right, so I can say hammer bracket Nick, hammer bracket Izad. And without the exclamation mark, it shows me the values that correspond to those keys. So computer science, electrical engineering, and so on. So we talked about a way to do for loops. We could say for variable in, and then have a list of things separated by spaces. Remember this, and it'll assign variable this first value, do the body of the loop, then it'll assign it the second value, do the body of the loop, and so on. So we can do that to iterate through the keys. So let's say 4K in $ parentheses hammer bracket @ do. And let's just echo what that key is. There's a probably 35% chance this will blow up. Hey, that worked. So now I've got a for loop that's showing me the value of each key in my array. And there's probably a 60% chance this will blow up. But let's print out the key along with the value of the associative array associated with that key. So $ curly hammer bracket $K. Hey, it worked. I'm shocked. So if this array stored my phrases, this is how I could do my print routine. Right? It's not sorted, but this would give me each key and then the data associated with it. And anytime we have something like this, there's always some way to iterate over the keys, so you can pull them out because they're not sequential. So we have this. So this is a list of data values. And this is a list of keys. And so this is also called a hash. And we'll study hashes in 222 in detail. We'll implement them from the ground up, and we'll use them in 223. But a hash is basically a way to take an arbitrary key and turn it into an index that you could use to access, say, a traditional array. So basically what's happening is internally, when I ask for this entry izad, that string izad is being transformed into a number, right? And internally there may be 127 entries in an array, and izad is turned into the number 17. And the entry for izad is stored at location 17. So when I ask for hammer bracket izad, internally it says, okay, if I've got this, this will be stored at location 17. He goes to location 17, says, what's the key that's stored here? It's izad. What's the data there? It's EE, right? And it pulls out the value from there.
Weird question. Can we pair this with regular expressions? So anything that ended with like ZAD would give you...
You'd have to do a little work, but you could. What you could do is right, you could take this and you could search for pieces of this that end with ZAD, right, and take each of those and then use that as an index. So you could do it. I don't think there's a very direct way, but yeah, definitely. So like I say, 222, and in 215 we talked about this a little bit in number theory, but in 222 we'll spin these from the ground up. But basically we take the arbitrary key and we use it to figure out where this thing is stored in a conventional array, and then we just pull it out from there. So it's not really as magic as it seems, but it is pretty powerful.
So when it's printing, like for example, like keys onto the screen, why doesn't it print it like in the order that you made it?
The order is completely random, effectively. There's no guarantee usually that it'll come out in the same order. The reason being that these keys are being turned into numbers, right? And it's probably going through the array from beginning to end and finding each number that's associated with a key and printing it out. So we're seeing some artifact of the way that Izad and Nick and Tina are being converted into integer array entries. But generally the order is considered effectively random. Now if I cared about the order, right, I could store a key, but I could put a number in the beginning and I could increment the number each time I store something. And so the data I would store would be 1, oh no, 2, ME, 3, wow, or whatever the order was. And then I could reorder them like that, right? Because I can store any data I want with these. And in C and in Java, right, typically we won't just be storing strings, we might be storing an entire structure that might have, 5 or 6 different fields to it. Yeah?
Is there any way to check what number they're turned into?
Not easily. And so that gets into a really interesting topic for data structures, which is called information hiding. And the idea of information hiding is anything that the user doesn't need to know, they probably shouldn't have access to. So in a package that was written without information hiding, we could probably snoop around and figure out where these things were actually stored. The idea of information hiding is that if somebody comes up with a new version of Bash that stores associative arrays in some totally different way, user code should not break, right? Whereas if we knew that the first entry was always stored at location 5, we might write code that says, okay, let's print out location 5's value first, and that code might break. But you can go into Bash, you can figure out how it does this, and then you could write some code to find those indices. But the philosophy is you don't need to know that, right? So you need to know basis. All right, so end of section A, I started talking about sed a little, and we're out of time, so we'll start talking about sed tomorrow. There are 2 main topics are going to be sed and awk. And we'll talk about things you can do with this that may help you on PA5. I don't think you need to use them, but they can be helpful. Sed will give us a way to edit a file by using regular expressions largely, right, without having to actually go into VI and type in commands. It lets us put commands inside a single command. And awk will let us take a bunch of lines from a file and break them up column by column. So if we want to rearrange columns or throw away columns or insert things between columns, we can do that with awk. If we want to do systematic editing on a file's contents, we can do that with sed. So we'll start talking about those tomorrow, and we'll continue them when we come back from break, because they're actually whole programming environments themselves. And we'll see like a 5-line version of PA4 using awk. All right, so I'll see you next time.